Hi there everyone, this is Peter here, and I need to redeem myself and also redeem a formula that I've been really prescribing to everyone, and that is the work energy theorem formula. It looks like this. It's the one that says that the work applied, like this, the net work done, okay, on an object is equal to the change of the object's kinetic energy. And then what you do with the net work is you take all the income work minus expense work, and that should equal your change in kinetic energy, which is a half mass times the change in future velocity squared minus initial velocity squared. Be very careful not to do future velocity minus initial velocity squared. That's not what it is. Change in future velocity squared minus initial velocity squared, and that just comes from taking a half mass as a common factor out of the difference between the future kinetic energy and the initial kinetic energy. Okay, so this is where the formula comes from. And then usually what we mean by income work, or not usually, that what I mean by income work is work in the same direction, same direction as motion, or basically work that will help me move, while expense work is work that will reduce or work against my motion or the object's motion. So income work is work that will improve my motion, and expense work will be work that decreases my motion in that direction. So typically we work with things like objects on an incline. Okay, so for an object on an incline, and I can think of various objects, but let's take a basic object, I guess. An object on an incline. That object has various forces acting on it. Let's change some color. This funny green. It's not nice. So for example, I could have weight. I always have weight. I might have a force pulling it up this incline. I have my normal force. The normal force never does any work, and the specific scenario that I talked about, or that we looked at, also had friction. Friction is always expense work. It always takes away energy out of my system, and gravity in this case is then an expense work. So in this case we've got what are our income forces? Well, we've got force applied, we've got frictional force applied, capital F, and we've got the normal force that we won't consider, because normal force can never do any add or subtract any energy. And then we have weight. And now the work done by these forces, if I consider net work, the net work done is then equal to the work done by the work that produces an income of energy, that is the force applied. Okay, so work done by income is work applied. Work applied could be an expense. If I'm trying to stop something from moving, then I'm applying a force to stop it from moving. Then the rest were expenses. The rest was work done by friction and work done by gravity. Both of them were in the opposite direction. And then that will equal the change in the object's motion. Will cause a change in the object's motion, and that would be future velocity squared minus initial velocity squared. Okay, and then all I do is I substitute the values in. For example, the applied work done is force applied times delta x, the distance it is displacing along the direction of this force, minus friction. The work done by friction is always just friction times delta x. The work done by gravity is not in line with the motion, so we use gravity as the force of gravity is weight, so mass times gravitational constant gives me that weight. So mass times that's W times the displacement in the direction of the force is from here to here, okay, depending on how, if this is its displacement, if it was moving from here to there, then what was its displacement in an upward direction or in line? That would be the height. And if we have this angle theta, then this is the height is the opposite. I've got the hypotenuse, that's delta x. So I'm not going to go through everything. You probably have seen me do it anyway. So to get that, this is the formula for the work done by gravity, or just mass times gravity times delta H, the change in height, which is also the potential energy formula. Okay, that's the work done by gravity. And then this is equal to, well, that formula again. This formula's got everything in it. So this is great. This is really a formula that's got almost all the values. The only unknowns it doesn't have in is time. Okay, so for example, I don't know how much time there passes between this point and that point given all of the values. And I'm going to have to, it's probably possible to just change the right hand side of this equation to actually have time in it, because it's definitely, the right hand side could be changed to just become, in some other settings, it could become, what was it? It's net work done. That's the formula. Net work is the net force times delta x. Net force is mass times acceleration. So we've got mass times acceleration times delta x. Okay, that's obviously, and the net force is always in the direction of displacement anyway, or opposite the direction. Okay, but that is mass times acceleration. And acceleration times delta x. Is there a way that we can put time in here? Well, delta x is equal to mass times acceleration. Delta x can also be represented by initial velocity times time plus a half acceleration times time squared. So you can definitely work with this formula even more to even include values like acceleration, which it doesn't have originally, but then you'll have to format this equation quite a bit, or just changing delta x, and then we've got acceleration and time in here. Okay, nevertheless, I don't want to go too much into the formula. There's videos where I've explained this over and over, especially with my students. So it's really a powerful formula, and I literally use it in everything except collisions. And so I had the confidence to approach a problem, this specific problem actually, and very confident stating to my students that I can use it without ever even having practiced it on a question like this. And I think I made a fool of myself. Maybe not. Not really, but I definitely made some serious errors, and I actually, strangely enough, figured it out in the shower this morning. So I wanted to just share with everyone how we could even use this powerful formula, this powerful idea that my income energies minus my expense energies equals the change in my kinetic energies. How we can use it to find even the tension in this rope. You can't see my T there. I can even use it to find the tension in this rope. Let me just move to this question now. Okay, so here we've got a scenario. In this scenario, I'll quickly read through it. We've got a block of mass 1 kilogram. There's this 1 kilogram block. It's connected to another block 4 kilogram with a light inextendable string, which just means it's light and inextendable. The point being that if the rope's weight doesn't make a difference to the system, and secondly, it's inextensible. In other words, the moment that the 1 kilogram block moves, the 4 kilogram block moves, which just means that they will have the same initial and final velocity. If this was a string that could stretch, then block 1, for example, the 1 kilogram block would start moving until it has stretched to its maximum length, and then block 4 would only start moving. So just the point being that the initial velocities of both would be the same, and also the final velocity. Okay, when the one stops, the other one will stop. The system is pulled up a rough incline of 30 degrees to the horizontal by means of a 14 Newton force parallel to the plane as shown in this diagram. Okay. The magnitude of the kinetic frictional force between the surface of the 4 kilogram block is 10 newtons. The current friction of friction on the 1 kilogram block and the surface is 0.29. And then the first question was, there's a few questions in between, but the first question just asked us to calculate the friction that the 1 kilogram block would experience. And just quickly to do that, because we need it in our second question where I actually want to use my formula, is to get frictional force using the coefficient of friction. It's coefficient of friction times the weight, which is mass times gravity, and then cos of the angle between of the incline. And where this comes from, it's the formula is actually mu times the normal force. And so our mu is 0.29, mass is 1, gravity is 9.8, and then cos of theta, which is 30 degrees. If we calculate that, we've got 0.29 times 9.8 times 30 cos is equal to 2.46. That's 2.46 newtons. That's the force of gravity that this first block would experience. Okay, now I just want to show you how we could use our this powerful formula of change in kinetic energy is equal to the net work done, or net work done is equal to the change in kinetic energy. And what I'm going to do is I'm just going to consider each block by itself. So I'm going to look at this block, I'm going to consider all the forces acting on this block, and then I'm going to look at the other block, and I'm going to consider all the forces acting on this block, or all the energies working in on this block, and then we'll use both of those formulas together to solve for the tension in the rope. So sorry, I didn't read the question, but the question asks us, calculate the tension in the string connecting the two blocks. So here's the string connecting the two blocks. We need to calculate the tension in that string. So let's start by just looking at all of the forces acting on block 1. That's going to be helpful. On block 1, we've got the weight of block 1. We've got a normal force on block 1. We've got the force applied, the 40 newtons, the force applied on block 1. And then we also have friction, which is in the opposite direction. And then we've got another force here, and that's the force in this rope. Okay, the force that this bottom the bottom block is almost pulling on the top block as it's being pushed upwards. So there's a force in that, and the force that this bottom block is applying to the top block is the tension in that string. Okay, that is the tension in that string, just like the tension in this string is the force that is being applied on this string. So that's T1. Now this is the tension in this string. Okay, so these are all our forces. Let's quickly look at what is our income energies. What helps this object to move as it's being pulled up? The only energy that, or force, that's helping is work applied. The rest are all expense energies. Now it's only looking at block 1 now. So expenses would be work done by gravity and work done by friction, as well as the work done by this force here, this tension in the rope. But all of these forces will still change the kinetic energy of block 1. Okay, and then what we have in, if we substitute values, the force applied is 40 newtons. Okay, work applied is, actually let me do it like this. Let's just substitute in like this: force applied times delta x minus gravity would be the force of gravity, which is weight, times the displacement along the height, this height. Okay, and this height I will get by taking delta x sine of that angle 30. Okay, the next is force of friction. In this case we did have friction, we calculated it in the previous question. times delta x. That's the work done by friction. And then finally, what's the work done by this tensional force? Well, tension is what I'm trying to find. Okay, I'll have delta x there, and then finally I will have on the other side half my mass times the future velocity squared minus the initial velocity squared. Okay, this will be the change in kinetic energy. Okay, now the one thing that we'll do now is we'll just go and look at the second block. If I look at the second block, I can first just consider all the forces acting on it. There's a downward force of weight. There's an upward pull. This upward pull is not the force applied on the whole thing, that 40 newtons. It's just the force applied by the string, which is the tension of that string. And then we've got friction as well in this one, and we've got the normal force. The normal force don't do any work. And so what we get, what are the income energies in here? The only thing helping this thing to move is the tension in this rope. Okay, so the tension that was stealing energy from the top block, it's stealing energy because it's giving that energy to the bottom block. So in the bottom block, that's an income energy, the work done by the tension. And the rest are all stealing energy. So that's gravity and friction is stealing energy. It doesn't have another rope connected to it. So that's why it doesn't have this extra one that the top one has. And this will also change its kinetic energy. Its kinetic energy will have a different change. But one thing that we can know, okay, so here we still have T delta X minus the weight is that one's weight times delta X sine of 30. 30 degrees is equal to the change in kinetic energy, which is a half mass times future velocity squared minus initial velocity squared. So we see we just have two extended formulas, but what I do want to show you here that is very important and that's very helpful is that the one thing that these two formulas have in common, okay, is the fact that the future velocity and the initial velocity for the two objects is the same because they're connected with the string. If they start from rest, both started from rest, the moment one starts moving, the other one will start moving because they're connected with this inextendable string, which means that these two factors are the same. And now whenever I have an equation where on the one side I only have one term and I've got in that term two factors to be the same, probably the best thing to do is just to divide those two formulas with one another, because that just gets rid of this completely. And that's exactly what I'm going to do. So I'm going to take all of these values, I'm going to substitute it, and at the same time I'm going to divide with this fraction. So I'm dividing the left hand side of this equation with the left hand side of that equation, the right hand side with the right hand side. And let's see what we get. So here our force applied was 40. We don't know how far it moves, but notice this, that every single term except for the right hand side has a delta x in. In the bottom, every single term has a delta x in. I forgot to put in friction, sorry. Okay, so every term has a delta x in, and since this is going to be a fraction, I can take delta x out as a common factor just now. So you'll see this works out beautifully. I love it. Okay, so we've got 40 delta x minus this. Now this top one's weight is his mass, which is the mass of the first block, is 1 times 9,8 times delta x sine of 30. Sine of 30 is just a half, minus the friction that he experienced was 2,46, what we calculated before, times delta x, minus t delta x. I don't know what t is, and I don't know what delta x is, but that's okay. We're going to sort that out pretty soon. Okay, so the left hand side, I'm going to divide with the left hand side of my second equation. Okay, and then we get the t delta x again. T delta x is unknown, both of them. This one's weight is 4 kilograms. Delta x is still unknown. Weight is 4 times 9.8. 4 times 9,8. The delta x is still unknown. Sine of 30. because it's on an incline, minus the friction that this one experienced. I remember from the question, it says that friction is 10 Newton. The magnitude of the kinetic frictional force between the surface and the 4 kilogram block is 10 Newtons. So minus 10 Newtons times delta X. That's the only income and expense energies for the bottom one. Now that would be equal to, and now on the right hand side we're going to divide these two terms, but notice these two are exactly equal because both of them will have the same future velocity and the same initial velocity, so they're just going to cancel. And the other thing that's going to cancel is this half. If I take this fraction divided, or this term divided by that term, the halves can cancel out. So I'm left with, and I can't cancel the masses because they have different masses. I should have numbered this as mass 1 and this is mass 2. Nevertheless, I get two different masses, and the first one's mass is 1 kilogram and the second one's mass is 4 kilogram. That's in the end what's left. Okay, so what I want to show you here is that if I have two objects with one force acting in on two objects connected to a rope, what I could say is that the net work done on object 1 is divided by the net work done. In other words, the ratio between the net works is equal to the ratio between their masses. I'm going to call this Peter's ratio. I think that's just awesome. Probably someone else figured it out as well, but no one told me that. I figured it out by myself, so I'm going to claim this formula for myself. Okay, and that's not specifically got to do. That doesn't always work with it in any scenario. Well, there might be more scenarios. I haven't tested it, but it definitely works when I'm pulling two objects up an incline. Okay, then this is what I have, and then that's exactly what this simplifies to. That's the net work done divided by the net work done on that one, and the simple reason for this is because the formula for kinetic energy, the future and the initial velocities of the system would be the same, and so that factor cancels out, and when it cancels out together with the halves, I'm just left with my masses, and so that's why it's true. And now we can simply continue to go and simplify this whole thing. Now it is a slightly complicated equation to solve. There's two t's that I want to get rid of. I still need to get rid of this delta x, but getting rid of that delta x is very easy. I take it out as a common factor from every term up here and from every term down here, and then it just cancels out. So I'm not even going to do that step. That's maths, and I'm not going to focus on maths in this lesson, but I end up getting the following, that 40 minus, and this is a half, so this becomes minus 4,9, minus, this becomes 2,46, minus t delta x, I now cancelled. Okay, so that divided by, in the bottom, I took out a delta x, and in the end it cancelled. So in the bottom I'm left with t minus, again sine of 30 is just a half of 4 is 2, so it's 2 times 9.8 is 19.6 minus 10 is equal to a quarter. Excellent. So again, simplifying towards the next step, I get 40 minus, well, I suppose let's use our calculator just to be sure. So we've got 40 minus 4.9 minus 2.46 is equal 32.55. 32,55 minus t divided by t minus 29,6 should equal a quarter. Now most people are like, oh man, come on, how do I solve that? Well, it's in an equation with a fraction, I always multiply with the denominators on both sides, or every term actually. So I multiply that on both sides, and I also multiply t minus 29,6. I multiply that on both sides, and I also multiply with a 4 on both sides. And then I see on this side these two terms cancel, or factors cancel. Here the 4 and the 4 cancels, so I've got 4 times 132,55, What is that? That is 120, 130, 130, and then 5 times 4 is 20. So 130, 20, I think so, minus 4t is equal to, and then here we only have t minus 29,6. And now when I solve for t, I can add a 4t on both sides to get a 5t on this side. So I've got 5t, and then adding 29,6 on both sides, adding 20, why aren't you working? 29,6 on both sides. I get 5t is equal to 159,8. Again, I did try this before and this doesn't look familiar, so I just quickly tested and I see I made a mistake here. This should be 32.64, 32.64 times 4 is equal to 130.56. So this is 130.56. Small errors, but I mean that makes a difference in the end. And then plus the 29.6 gives me 160.16. So just here in the end, 160.16, and then I'm dividing both sides with a 5, and that then gives me my final answer divided by 5. And this looks familiar. 32.032 tension is 32.032, and that is my final answer in newtons, and I'm fairly confident of that result. So just once again want to show you this the awesome power of the work energy theorem and how it just always applies. It's brilliant. It's really a wonderful little formula, and it leads to this result. Show it to your friends, Peter's formula. And it's not really my formula, it's just a basic result of dividing two elements or two objects that's experiencing the same applied force on both of them, and that's the result. So thank you for watching. I hope you enjoyed it. I hope you learned something, and hopefully next time you see me, we found something new that we can use to make things for us a bit easier. Bye.